I'm very glad to introduce our team project virtual keyboard. This is the user interface of our virtual keyboard. Firstly, I will discuss about improved affordance and feedback. As you can see, keys turn yellow as the mouse hovers over them. This implies the keys are actually buttons that the user could press on them. It also helps the user to recognize the current location on the keyboard. For a single click, the key turns gray and an audio cue is generated as the mouse clicks on the key. This denotes the button is pressed, thus the user knows they successfully typed their character. For sliding inputs, mouse trace is visualized as green solid line. This helps the user to recognize the current location when they slide over keys on the virtual keyboard. For sliding input, keys turn green if they are inflection points in the mouse trace, or turn yellow otherwise. This notifies the user that inflection points are different, thus be aware of them. Furthermore, audio cues are generated as soon as we detected inflection points. Spelling mistakes compared to the expected inputs would be highlighted. This feedback tells the user the mistakes that they made, thus urge them to correct. Characters turn green if they are correctly inputted. For the mistakes, actual characters are denoted as red dash, mistyped ones as red character, and missing one unchanged. Okay, let me talk about shorthand on virtual keyboard. The benefit for using virtual keyboard is that we can use the gesture typing, which means the end user slides finger on each intended key in a word one by one without moving up their fingers. In our design, we use a sequence input defined by sliding fingers or mouse. Our implementation is using the regular pattern recognition, regular expression pattern plus the natural language information. For example, if the user slides from T to E, we will generate regular expression pattern, including T and E as required character and R as an optional character. Using this regular expression pattern, we can match from the dictionary we have. Using this matching mechanism, we can find a list of candidates. In this example, the candidates include tree and T. Our problem became how to distinguish and apply the most intended input that user want to input. Our solution is to use the word frequency contained in the natural language dictionary. In this case, tree is a more popular word than T. Thus, we put tree in a easier to reach position than T. Even though we still grant the privilege to the end user to choose among all the candidates. Another example is cat. You can see we have 4 candidates, and if the user, there are 4 candidates and the cat is the most frequent one. If user want to input cat, he can click cat, or if he change his decision, he can select among the 4 candidates. Finally, let's talk about the performance measurement and the visualization. We use the Levenstein edit distance to measure the differences between the user's input and the expected input. To visualize our measurement in real time, we compute the distance after each time the user has typed a character. We use a backtrace matrix outputted by the algorithm to visualize the measurement. As in the measurement, correctly typed characters turn green. We leave the character in the same input unchanged if it is not typed yet. A red dash in the sample input is inserted if the user typed an extra character. The color of the character turns red if the user mistyped it. Okay, that's all for our introduction for our project. Please let us know if you have any questions.